Welcome back to the playlist on protein function, enzyme function. Some people have been coming to my sessions say they're having more problems with kinetics and thermodynamics of enzymes. So what I decided to do is do a series of videos on the kinetics and the thermodynamics of enzymes. Okay. Now, with kinetics and thermodynamics, we generally break it up between the two because they're completely separate animals. Okay, we're going to do kinetics first, and basically what kinetics is it's talking about the rate of the reaction. Okay, and one of the key features of the rate of reaction, there's two main things we're talking about. Okay, number one is the activation energy. So the activation energy is simply the energy that has to be input into the system in order to cause the reactants to move into the transition state. Okay, and we'll look at a diagram of that in a few minutes. Okay, and the other thing that we're looking at is the relative difference in energy between the reactants and the products. So the easiest way to understand this is really just to look at a picture. Okay, so what I'm drawing here is not really for any enzyme in general, but it's just for a very general reaction. It could be organic, could be biochem, whatever. Okay, so on the y-axis we're going to have our free energy G, and that comes from Gibbs free energy, by the way. And on the x-axis we're going to have a specific reaction coordinate. Okay, understand that the reaction coordinate is simply showing how the reaction is proceeding as we move in time, but there's not specific time that's on the x-axis. It's just showing that as we move across time, how we're proceeding, but there's not actual time units that are on this axis. So it's not technically a time axis, okay? But it does show us how we proceed with time, okay? So let's look at a hypothetical curve. Okay, so let's say I start with like this. I go up in energy and then I come down. And I come down to an energy like this. Okay, so the first thing you should notice about this curve is that these are the reactants right here. So we would say this is the free energy of the reactants, and then this down here is the free energy of the products. And the first thing that you should notice about this curve is that the reactants are higher in energy. Okay, this is one of two kinds of reactions that we generally have, and it's just where the reactants start off in higher energy than the products. Okay, now notice that we have to input some energy into the reactants to get them up to this point right here. This point right here is called the transition state, and it's generally given this sort of two-line dagger or whatever you want to call it. I don't know what that symbol is, but generally that's what the symbol is for the transition state. And the transition state is really just the intermediate in the reaction. Intermediates are generally very unstable. They don't last very long once you form them. So in other words, if I was to input the energy into the reactants to get them to the transition state, you would either go backwards towards the reactants or towards the products. Generally, it's going to be towards the products, but basically understand that it's not going to last very long at all. Okay. And also, as a result of the fact that they don't last very long and the fact that they're unstable, intermediates are difficult to measure. Okay, and that's something that can be important if you're doing particular studies. So usually, if you are trying to actually measure the intermediate, you get the intermediate in terms of something else just because it's very difficult to measure. Okay, now the energy that I have to put into the reactants to get them up to the energy of the transition state, that's called delta G of activation. Okay, so we generally denote it with the activation, or excuse me, with the transition state symbol, and so this is delta G of activation. A lot of times you'll hear this referred to as activation energy. Okay. Actually, normally, ordinarily, you'll hear it referred to as activation energy. Okay, but in reality, it's just the free energy of activation. So if you're looking at a free energy diagram, it's the free energy that you have to input into the system in order to get this reaction to go. Okay. Now, one important thing about activation energy is that the higher the activation energy is, the slower the reaction becomes. And we're actually, maybe not in this video, but in another one, We're going to look at why that is. But suffice it to say for now, as the activation energy of a reaction increases, the slower the reaction becomes. Okay, and one thing we'll find that enzymes do is they actually lower the activation. They lower the activation energy by providing an alternate pathway to the products. Okay, and we'll see what that means in several videos. Okay, now one important thing that comes out of this reaction is that notice that the products are lower in energy. Okay, so another way we can define the free energy of the products is the final free energy, and one other way we can define the free energy of the reactants is the initial free energy, right? So if you were to take delta G of this reaction, right? If you were to take delta G of this reaction, you'd have what? You'd have the final free energy minus the initial free energy, right? So if you were to actually do this for this reaction, right, are you going to get a negative or positive value? Well, in other words, your products, the free energy of your products is going to be a lower number than it is for the free energy of the reactants, right? So if you're taking a small number minus a larger number, assuming they're both positive, you should expect to get a negative delta G value. Okay. Now, there are several important things that come out of saying a reaction has a negative delta G. Okay. Number one, we say that this particular reaction is spontaneous as written. The other thing that comes out of saying something has a negative delta G has to do with the fact that, or has to do with, well, first of all, let's look at this. Okay. So if we look at the difference in energy between the reactants and products, okay, we have a net release of energy. Okay, so that's actually one of the other things that comes out of saying something has a negative delta G is we have to, or we actually get energy released. Now, one thing I want to make perfectly clear, because this is an area of confusion, okay? Now, it is true that we have to input some energy to get it to the transition state. So in all reactions, it doesn't matter whether it's negative delta G or positive delta G, okay? You're going to have to input some energy, okay? But when we say that when we have a negative delta G, when we say we have a net release of energy, it means just that. It is a net release of energy, okay? So you always, regardless of whether it's negative or positive free energy change, whenever you're going to have to input some energy to get at the transition state, right? But in negative delta G reactions, you have a net release of free energy. Okay, so you have a net release of free energy, and often that's used to drive work and drive other reactions. Okay, so you have a net release of free energy, even though you have to input some energy to get to the transition state. Now, as we'll find with positive delta G reactions, you have to have a net input of energy. Okay, but in a negative delta G reaction, you have a net release of energy. Okay, and another name that we can give reactions with a negative delta G is exergonic. Okay, this is not to be confused with exothermic. Exothermic means something has a negative delta H, has a negative change in enthalpy. Okay, when you say something has a negative, when you say something is exergonic, it has a negative delta G. Okay, so the important things to be able to tell from one of these diagrams is what's the intermediate, okay, the transition state, in other words, being able to tell if the products are lower in energy or higher in energy, right, knowing what the activation energy is, and then just knowing in general what the difference in energy between the products and the reactants is. And if your products are lower in energy, you have a negative delta G. Okay, let's look at another example. Okay. A second example, and you can probably guess where we're going with this. Okay, so our reaction and coordinates on the x-axis and our free energies here. Let's say, let's do this in blue. Okay? Let's say that I have something that looks like this. Okay, so again, the very first thing you should see is that the free energy of our reactants, or our initial free energy, is lower than the free energy of the products, or our final free energy, right? So if I were to express the delta G of this reaction, you basically, again, say it's the final free energy, in other words, of the products, minus the initial free energy, okay? Now, what you're doing is you're subtracting a number minus a smaller number, right? So you would expect, in this case, for delta G to be greater than 0, okay? Now, let's look at a few things. Number one, again, we identify our transition state or our intermediate, and just remember that those molecules that we get are very difficult to measure. Okay, they don't last long. They're very unstable. And just remember, things that are higher in energy are unstable. So that's actually something that's really important. If you increase the energy of something, you are decreasing its stability or increasing its instability. Okay? So high energy things tend to be unstable. Low energy things tend to be more stable. Okay? So you could look at this diagram and you could say that the reactants, where you have the initial free energy, the reactants are more stable than the products, and that's because the reactants are lower in energy than the products. Okay, but overall this reaction has a positive delta G. Now what we can do is we can look here and we can say, okay, well, this right here is the free energy of activation, right? So this is delta G with the dagger, right? And so this is your free energy of activation. And remember, the free energy activation, if we're assuming we're moving from left to right, it's just the difference in energy between the reactants and the transition state. Now notice something between these two reactions, okay? In this case, assuming we're going by the same units, right? Assuming that the size of the arrows means that, well, assuming the size of the arrows means that this particular free energy of activation is smaller than this one, right? Notice that this one has a larger free energy of activation, okay? So what we would say is that kinetically, this reaction would be slower. So what you would find is that the larger the activation energy you have, the slower the reaction becomes. Now that is a kinetic term, okay? The speed of the reaction is kinetics, okay? So the larger the activation energy, the slower the reaction. Now, you cannot say, okay, through kinetics, okay, whether a reaction is more thermodynamically favorable, okay? The way you tell whether a reaction is more thermodynamically favorable is by the sign of delta G, okay? So let's say I have two delta G's. Okay, let's say I have two delta G's. One of them's, let me do this. Let's say I have one delta G that's negative 30 kilojoules per mole, and let's say I have another one that's negative 20 kilojoules per mole, right? And I ask you which one's more thermodynamically favorable. Well, you'd say this one, right? It's more exergonic. So the larger the delta G, or I should say the larger the magnitude of a negative delta G, in other words, the more negative it is, the more favorable it is thermodynamically. Now notice I said thermodynamically. So what if I asked you this question? Between these two reactions, which one's more kinetically favorable? And your answers should be, you can't tell, right? So in other words, what I'm trying to get across is that you can't tell whether something's more kinetically favorable than another reaction if you're given delta G's. Okay? In other words, the delta G I'm talking about is the difference in energy between the reactants and the products. Okay? If you're just given that delta G, in other words, that's this delta G. Okay? This delta G, right? In other words, it's this delta G I'm talking about. If you're given the delta G of the reaction, right? Not the activation energy, but the delta G of the reaction. If you're just given that, you cannot tell what's more kinetically favorable, okay? You can only tell which one's more thermodynamically favorable. So according to thermodynamics, this one is more favorable because it's more negative. However, if I just give you these two pieces of information, you cannot tell which one's more kinetically favorable. So you can have two reactions. One of them, let's say one of them is negative 30 kilojoules per mole, right? I could give you another one that's positive 30 kilojoules per mole, right? And so which one's more favorable thermodynamically? It's the more negative one, right? It's the exergonic reaction, right? But if I asked you which one's more kinetically favorable, and these are delta G of reactions, right? You can't tell. It might very well be that even though the positive 30 kilojoules per mole, even though that one's more thermodynamically unfavorable, or we could say even though it's non-spontaneous, or we could say it's not thermodynamically favorable, it still could be kinetically faster. So one important point that comes out of these reaction coordinates is that you cannot tell you cannot tell if something's kinetically favorable from thermodynamic data. Okay, so in this case, okay, the delta G of the reaction right here, that's a thermodynamic quantity. The activation energy tells you the kinetics of the reaction, and those two do not go together. They do not depend on each other. Okay, really, the thing that dictates the activation energy, free energy, is the transition state. The only thing that affects the delta G of the reaction, this, is going to be the difference in free energy between the reactants and the products. Okay? Now, again, like we had for the negative delta G reaction, there are several things that come out of a positive delta G. Number one, you have to have a net input of energy. Now, remember for this one, for this reaction, I said, yeah, you have to input energy to get up to the transition state, but you have a net release of energy, right? In this case, again, like all reactions, you have to input energy to get up to the transition state, but notice that the free energy of the products is higher. So ultimately, you have a net input of energy, okay? So this delta G is positive because you have to have a net input of energy. We're defining things with respect to our system, which is our reaction. So if you want to get this reaction to go to completion, you're going to have a net input of energy, okay? And another thing that we can say about this reaction is that it is non-spontaneous, okay? Non-spontaneous means it has a positive delta G, and we can also say that it is endergonic. Okay. Again, that's not to be confused with endothermic. Endothermic means you have a positive delta H. Endergonic means you have a positive delta G. Okay. Now, one thing I do want to mention about these particular these pieces of terminology, exergonic versus endergonic. Okay. You might be tempted to say, okay, if you've got something that's thermodynamically favorable, you might be tempted to say that it's irreversible. Well, that is not the case. Okay, just because something is spontaneous and it has a negative delta G doesn't mean that it's irreversible. Okay, in a lot of cases, things with negative delta G's in biochemistry, they could be exergonic, but they're reversible reactions, so they'd correspond to an equilibrium, right? So you can go either direction in the reaction, even though it has a negative delta G. Okay, likewise, just because something's endergonic doesn't mean it's reversible. Sometimes you have endergonic reactions that are irreversible. There are some that are reversible, but the point is that not just because something's exergonic or endergonic does not dictate the one-way or two-way directions of a reaction. Okay, and just like when we talked about activation energy, you can have something that is thermodynamically favorable, and it still takes a very, very long time, even years. Okay. One of the reactions, don't quote me on this, but I believe that a rhododilate decarboxylase, is a spontaneous reaction. Okay, a rhododilate decarboxylase is an enzyme that removes a carbon dioxide from a molecule called a rhododilate. It's in pyrimidine biosynthesis, and I believe it has a negative delta G. However, in the absence of any enzyme, okay, the reaction takes like 77 million years, okay, and the enzyme does it in about 17 milliseconds, okay. So we would say that thermodynamically it's favorable, but it takes a hell of a long time. Okay, it's never going to happen basically under normal conditions. Okay, so you can have thermodynamically favorable processes, but they're not going to happen very fast. Okay. Okay. Likewise, you can have an endergonic reaction, right? You can have an endergonic reaction that takes a shorter period of time than the exergonic reaction. Okay, so kinetics and thermodynamics have nothing to do with each other. Okay, kinetics is a function of the activation free energy, and thermodynamics is a function of the difference in energy between the reactants and the products. Okay, that's the delta G of reaction. Okay, now let's talk a little bit about enzymes and how they affect this. Okay, so we're just going to do a generic exergonic reaction. Okay, so one thing enzymes do is, okay, let's say we have a reaction like this, okay? So we have a reaction like this, okay? One thing enzymes do is they do not change equilibrium, okay? That is a very, very important point. Enzymes have no effect on equilibrium, meaning that the free energy of the product or reactants doesn't change, and the free energy of the products doesn't change. So in other words, the free energy of the reactants and products is not affected by the enzyme. Okay, what the enzyme is doing is changing the kinetics of the reaction. Okay, so what the enzyme effectively is doing is just lowering the activation energy by providing an alternate mechanistic pathway. Okay, so what you have is the enzyme is basically going to do something like this. Okay, so you're going to start at the same energy. Okay, but it's going to break the reaction up into a series of steps that lead to the same free energy of the products. Okay, so what you can do is so basically this would be a reaction mechanism. Okay, and each one of the steps of the mechanism has a corresponding transition state, right? So you could say here's a transition state, here's a transition state, and here's another one, right? So there's 3 humps, so there's 3 transition states, right? And each one of them is going to have a free energy of activation. Now my question to you is, which one has the highest free energy of activation? Well, you say steps 1 and 3 are kind of the same, but it looks like this one right here has the highest difference in energy between the transition state and the original energy, which would be this right here, right? So basically what you're doing is you're looking at the difference in energy between this point and this point. Likewise, if you're doing it for the 3rd hump, you would be looking at the difference in energy between this point and this point, right? So you're just looking at the difference in energy between the material you start with and the transition state. And again, we define that as delta G with the little dagger, so it's the free energy of activation. And so that second step, right, the second step of this mechanism has the highest activation energy. So when you look at what an enzyme does, okay, the step of the mechanism that has the highest free energy of activation is going to be your rate determining step, okay? Rate determining step. Another terminology that you might hear is the rate limiting step, okay? Now, one thing to be perfectly clear about, it depends on when you're watching this video. If you're probably watching this video, you haven't really seen anything on metabolic pathways. Now, for instance, glycolysis is a reaction scheme that has 10 enzymes, okay? Now, there are 2 contexts in which rate determining steps are talked about, okay? You can have rate determining steps for individual steps in one enzyme's mechanism, okay? That's what we've seen here, okay? So the rate determining step is the free energy of activation for step 2, right? But you can also have rate determining enzymes, okay? And that's just the slowest enzyme in a reaction scheme. That has nothing to do with this, okay? So that's just some area of confusion sometimes. When you're saying the rate determining step of one enzyme, you're talking about the slowest step of the enzyme, okay? So in the mechanism of the enzyme, there are multiple transition states. The state with the mechanistic step with the highest activation energy, that's your rate determining step in the mechanism. Okay, and just remember that the enzyme itself has absolutely no effect on changing the free energy of the reactants and no effect on changing the free energy of the products. It doesn't do that. It's simply changing the activation energy by providing an alternate mechanistic path. Okay, understanding the mechanism is not the point here, or it's not really important as of now. Just understand that basically what you're doing is you're distributing the increase in free energy into smaller steps. So you can imagine it's a lot easier to do this small step, this relatively small step, and this small step than going over this giant hump right here, which would be in an uncatalyzed reaction. You'd have this delta G, right? This delta G of activation is much higher than this one, right? So it's kinetically faster to do it in multiple mechanistic steps, each with a smaller free energy of activation. So what we can say is that an enzyme is a biological catalyst. And there are really 2 types of enzymes. There are RNA enzymes, which are not as common. In general, what we're talking about are protein enzymes. So you can effectively say that enzymes are proteins that speed up kinetically biological reactions by lowering the activation energy by providing an alternate mechanistic path. Okay, So one of the main points to understand is be able to determine, does something have a negative or positive delta G and what that means, okay? And then being able to apply it to something like this, and understanding that enzymes do not affect the equilibrium, and they do not affect equilibrium. They simply affect the kinetics. They have no effect on the relative energies of the reactants and the products. In the next video, what we'll do is we'll look at some of the equations that can explain some of this. See you in the next video.